Now we're going to look at Chapter 12. This is actually Chapter 12 in the new book, at Reactions of Arenes. There's two variations of these reactions. The first we're going to look at are reduction reactions, where you're going to actually involve the ring itself. And then you're going to have other reactions that the ring is used as a substituent. So let's look at the reduction reactions first. When you do a reduction reaction, you're going to break the stability of the benzene ring. So we already saw one of these in an earlier part of this chapter where you did a catalytic hydrogenation of the benzene with 3 moles of hydrogen in the presence of the platinum catalyst to form the cyclohexane. The first one we're going to look at this portion of the chapter is called the Birch Reduction. In the Birch Reduction, it's going to involve a group 1A metal, liquid ammonia, in the presence of an alcohol. This reduces the stability of the benzene ring by forming a 1,4-cyclohexadiene derivative. So you can see it here. So here you've got your benzene, your sodium, which is a group 1A metal, your ammonia, and the alcohol. So let's look at the mechanism. The first step is an electron transfer from the sodium. So sodium, remember, is a group 1A metal, has a lone electron. It's going to send that one electron here. That's going to rotate these pi electrons to this position. These pi electrons are going to be rotated to this position. So you're going to end up forming what's referred to as an anion radical, because you have a negative area and a free radical in the same compound. Your sodium is going to become an ion because it's lost its one electron. The second step is going to be the proton transfer from the methanol. So you're going to take, here's your methanol down here. Your methanol is going to break this bond between a hydrogen, the OH hydrogen, and create this ion. And this hydrogen is going to link up here to this region of this, what used to be a benzene ring, but now is the anion radical. Okay. So now this simply becomes a cyclohexadienyl radical, because you only have the single electron here and not the pair of electrons down here like we had before. The third step is kind of a repeat of the first step, just with different parts of the molecule. So we're going to use, again, an electron transfer from sodium. So you have a sodium atom again. It's going to send its one electron here. You're going to create an anion again this time. So your cyclohexadienyl radical becomes a cyclohexadienyl anion, and you form another sodium ion. And then the last step is like the second step, where you're going to do another proton transfer from the methanol. So here's your methanol up here. There's the bond that's going to break. This hydrogen is going to go here. These electrons are going to pick up that hydrogen and create this, which is now the 1,4-cyclohexadienyl molecule. Now, if you have an alkyl group that is present on the benzene ring and you carry out the Birch reduction, the main thing you got to remember is that the double bonds of the 1,4-cyclohexadienyl one of them has to touch the carbon that this alkyl group is attached to. So this would be appropriate, whereas if I had written it and put my double bonds, let's say, oops, I did that backwards. I'm going to do this real phone. Here and here, and then had my structure here, then this would be incorrect, because my double bond is not attaching to the carbon that has this alkyl group on it. Now the next reaction we're going to look at are going to be dealing with Alkylbenzenes or benzylic carbons. A benzylic carbon is going to have, if you come down here and look, it's going to be like the benzene ring with a carbon attached to that benzene ring. So that would be your benzylic carbon here. It can be a carbocation, it can be a free radical, It can be just a regular molecule, but we're going to be looking at the benzylic radical reactions in this particular case. The first reaction we're going to look at is called a free radical halogenation of the alkylbenzene. So you're going to add halogens to the benzyl, what they call the benzyl carbon. It can either be a chlorine by the Cl2, it can be a bromine by the Br2, or you can add the bromine using the normal bromosuccinimide. You'd also use the solvents that we have used in the past. So this is just showing you the resonance of the benzyl radical. It is going to have like a allylic group right here. So this radical, if you do the allylic rearrangement, you're going to come down here. This will be where your free radical would be in the ortho position on the molecule. If you take that one and do another allylic rearrangement, you'd be in the pair position. If you do the next one, that'll be in the ortho position. So you can see that you're going to have ortho-paired type of situations on this molecule. If we look at the free radical chlorination of toluene, here's toluene with the methyl group attached to the benzene ring. You're going to use your chlorine, your light, or you can put the H sub nu there, and the heat. As long as you have chlorine molecules and you have benzylic hydrogens, you can remove every single hydrogen step by step. So my first reaction, of course, with 1 mole of chlorine will be to remove 1 hydrogen. My next step, if I had a second molecule, I could remove a second hydrogen, and then if I had a third mole, I could remove a third hydrogen. So I could remove all the benzylic hydrogens and eventually form this molecule. Here's the benzylic bromination. So here's your bromine. This is a paranitrotoluene. So just remember, just like before, this is an ortho paradirector. This is a metadirector. But it doesn't really matter in this particular case because we're not attacking the benzene ring. We're looking at the benzylic carbon. So we're going to only affect the benzylic structure up here. So my benzylic hydrogen is going to be replaced by a bromine. The benzene ring is not going to be affected in any way. And, of course, our hydrogen that came off here is going to be picking up the second bromine in this molecule. You can do the same reaction using your normal bromosuccinimide. You're going to, again, this is your benzylic carbon. So the benzylic hydrogens here are what's going to be affected. So I can remove one of those hydrogens, replace it with the bromine, from the normal bromosuccinimide and form this compound. So this is the free radical halogenation of an allylic benzene, or on the benzylic carbon. The next one is an oxidation of alkylbenzenes. And this one you're going to use chromic acid. Chromic acid is H2CrO4, but we typically are going to use it in this format because this is going to form it. So this is our sodium dichromate, water, sulfuric acid, and heat. What this is going to do is going to remove the benzylic hydrogen and carbon group and replace it with an acid group, or a COOH group. It doesn't matter how long the group is, as long as it's got the benzylic carbon. If you have any kind of a carbon group off the benzene ring, it will replace that entire group up to the benzene ring itself. So if we look at this example, here's our benzylic carbon. Here's our substances that make our chromic acid, and you're basically going to replace this methyl group with our carboxylic acid group. If I have 2 functional groups, but I still have benzylic hydrogens on both of them, then I can replace both of these with the carboxylic acid group. Now the next thing we'll look at are SN1 reactions of the tertiary benzylic halides. These are nucleophilic reactions. There are no rearrangements in this particular type of reaction. So we're going to skip through a few of these things. We've got these PowerPoints. Again, just like we saw earlier, the benzylic carbocations are going to be orthopara. So here's an example of your reaction where you have this alkyl group. It's got a halogen on it. You're going to remove this halogen, create the positive carbocation. If an alcohol is added, then you're going to break the hydrogen off and add this on, so you're going to actually form an ester. So these are some reactions that you're actually going to see in Chapter 8 of this textbook. So these are just kind of some quick reviews. This one is using a SN2 mechanism with a primary benzylic halide. So you're basically going to do similar, all the same types of reactions for the primary, secondary, tertiary. The mechanism is what's going to differ just slightly. So if you're looking at this one, you'll take your primary benzylic halide, remove that chlorine, break off of this molecule your sodium, and this oxygen is going to attach here. In this case, you're going to form an ester. So these are going to allow you to form a lot of different substances by nucleophilic substitutions. This just shows you some examples of some of the practice problems you can use. So you could use sodium ethoxide with your molecule here that's a benzylic halide. You'll break off the sodium, this group will attach, and you'll have an ether. If you have this one, you have the potassium tertiary butoxide. So you have this, you'll break your potassium off, your bromine off, and you'll form this ether. This is using an azide compound. So you have these, this is your azide, or you could have like N double bond, N double bond, L double bond, either one will be fine. And you're going to, again, break off the halogen, break off the metal, and you'll form your azide compound. This one forms a thiol compound. So if you have a sodium hydrogen sulfide, sodium will come off, bromine will come off, and you'll form a thiol. If you want to put an iodine on the benzene ring or on a benzylic carbon, you're going to use the sodium iodide in the presence of acetone, and you'll get your benzyl iodide. So look at the various reactions that are on your reaction sheet. That should help you with the various types you can do on that. Now, if you want to make or prepare alkylbenzenes, these are going to be elimination reactions, and they're going to be just like the ones that we did for your alkenes. To making alkenes, you'll have a dehydrogenation. This again is one of those that's more on the industrial scale because it requires such high temperatures. But what it would do is basically remove a hydrogen from each of these carbons and create the double bond on the side chain of the benzene ring. If you do an acid catalyzed dehydration of a benzylic alcohol, then you're going to remove this is going to be your alpha carbon, which will be your benzylic carbon. It's going to remove, and then your beta carbon is going to be where the hydrogen comes off. So you can, again, can use sulfuric acid, phosphoric acid, potassium hydrogen sulfate as your acid catalyst, heat, and then of course your side chain is going to be where that double bond forms, or the alkene area. You'll also do the dehydrohalogenation. Again, this should be actually, okay, this is on the carbon here. So your beta carbons are here and here. It will follow the Zetsif rule in making these compounds. So you're going to put your double bond in this position in this molecule. And really this This is kind of got off-center. This should actually be over on this molecule. All right. No, I'm sorry, that's right. I had it right the first time. Now, addition reactions to alkylbenzenes, all of these are going to be the same as the reactions that we did for alkenes. So you can do the hydroboration, you can do the hydrogenation. So I'm just going to quickly show you some examples. So here's your hydrogenation here. Adding the hydrogen, you're going to break the double bond, add hydrogens to those carbons. Again, you need a metal catalyst, so your platinum and these are other acceptable ones. You do follow the additions rules, so this is a syn addition. Here's a halogenation with the bromine. You can do it with the chlorine as well. You'll get a vicinal to halide-like structure here off the side. And this particular one, you have your hydrochloric acid or hydrobromic acid or hydroiodic acid. Any of those would be acceptable. You're going to, of course, break this bond, creating an allylic carbocation, and of course, that's where the halogen would form, is on that region of the carbocation. If you use the hydrogen bromide with the peroxide, it's the free radical addition of hydrogen bromide, then of course this is going to be the antimarkovnikov and add the bromine on the less stable position from the free radical. I'm going to skip through that.